Hey everybody, my name is Yondon, and I am a software engineer and researcher working at LivePeer, which is decentralized video streaming infrastructure. The details of that project will come up a little later in the presentation, but the general theme of my presentation today is fair service payments in decentralized networks, and this follows up to Arjun's talk quite nicely in that we're thinking about some of the same problems, but I'll focus on two specific problems for this talk. And then when I say decentralized networks, primarily referring to decentralized service networks where some provider on the network is offering a computational service in exchange for payment. So the agenda for the presentation is as follows. I'm going to start off by setting the scene a little bit and talking about the setting that we're operating in for these types of networks. Then I'll go on to talk about two specific problems in the design space for these types of systems. First, defining what constitutes a fair payment, and second, how to begin to think about ensuring quality of service for the end user. Then I'll talk about some potential solutions to these two specific questions. So the first, defining fair payments via some resource metering mechanism, and the second, achieving quality of service via a combination of micropayments, redundancies, and failovers. And then we'll close out the presentation by talking about some interesting open research problems. So first, the setting. Generally, these decentralized service networks can be thought of as two-sided matching markets where we have service requesters that want some form of computational service performed and service providers that are offering that computational service in exchange for payment. And then within this market, we want some matching mechanism such that requesters can be routed to the correct providers that can ensure some minimum quality of service. So I think two things that are worth noting in this setting is that oftentimes when we're creating these systems, these service providers have quote unquote weak identities in that they're oftentimes identified by cryptographic key pairs. So they don't always have strong real-world identities associated with them. So usually you have to assume that these actors are going to be anonymous, pseudonymous, and you might not necessarily know who they correspond to in the real world. So you're vulnerable to things such as Sybil attacks. Second, some faults in these systems are not uniquely attributable. So if we compare these types of systems to, let's say, proof-of-stake-based consensus protocols, a common design in these protocols is to include slashable security deposits. And the reasons these security deposits can be slashed is oftentimes you can uniquely attribute a fault that's committed by a validator node to a specific identity. So let's say you double voted on a block, that's uniquely attributable. But in other types of service networks, it's not always the case that you can attribute every single fault. So you might be able to attribute a correctness fault to a provider if they actually perform the computationally incorrectly. But let's say that you have a situation where the provider provides slow service. Well, slow service is not necessarily something you can uniquely attribute to a provider, but it definitely impacts the end user if the end user expects a certain amount of latency in order to guarantee that their application functions. So ultimately, our goal here is creating a two-sided matching market with requesters matched to providers that meet the requester's quality of service preference. And what's interesting is that, at least in traditional economics and mechanism design, matching markets have been a popular area of study, and there have been efficient designs implemented in a variety of domains, such as medical residency matching or other types of labor marketplaces. But oftentimes, these efficient designs are achieved using some sort of centralized clearinghouse, which is going to aggregate preferences from both sides, and then, only then, will it execute a matching algorithm with the full amount of information in the market. So ideally, in these decentralized service networks, we want to try avoiding relying on trusted, opaque, centralized services to match parties. Although I emphasize trusted and opaque just because there is potential utility in having third-party matching services if you could design a mechanism such that they can be untrusted or transparent. So something I think is worth noting. And then finally, when we're designing these types of systems, we want to avoid relying on legal recourse in the event of an SLA breach, because if you're relying on legal recourse, that's something in the domain of traditional cloud service providers, and we want to try to design these systems where you don't have to rely on that as a backstop. So moving on to the problems. So problem number one, what constitutes a fair payment? So simple definition, really, a fair payment is going to adequately compensate a provider for the service. So the requirement here is that the provider should be able to ensure that it's adequately compensated for the resource costs it incurs for a service, because it wants to be protected against resource exhaustion attacks. Second, how do we ensure some quality of service? So generally, a requester would like a quality of service that is not dependent on any particular provider. What this means is that the requester shouldn't be negatively impacted if a particular provider fails for any reason, whether that be due to insufficient capacity due to overload, it's geographically distant because it doesn't have a distributed infrastructure set up, etc. So starting off with the first question. So one way that we can think about how to define fair payments is via resource metering. And what that means is that providers can have some mechanism where they can meter their resources and then charge requesters based upon the resources consumed. So a prerequisite to this is that you need to define a unit of measurement, which is how many units of a resource are actually being consumed by the task that's being requested of me. And then from there, you can define the payment value as the number of units multiplied by the price per unit. But this brings up a question: when should these units be measured? And it actually depends on the context. So I think it'll become a little more clear if we go through two particular case studies where resource metering mechanisms are implemented. So the first one, most people are probably familiar with, Aetherium. So in Aetherium, smart contract platform powered by an underlying blockchain, miners are executing computations defined by user transactions. But the tricky part here is that the miner can't determine how computationally costly a transaction is without actually executing the transaction. So the solution used in Aetherium is the gas model, where the unit of measurement is a unit called gas, and there's an associated gas cost with every single opcode used in the Ethereum virtual machine. So as a transaction is executed, it's going to use a certain number of opcodes from the virtual machine, and then the end resource cost is going to be denominated in gas. And users are going to define a gas limit for each transaction, and this is useful for the miner in that it presents an upper bound on the amount of resources that can be consumed by the miners. So it's okay if a miner doesn't know how costly it's going to be to execute a transaction ahead of time because it has this upper bound. So Ethereum uses this global metering model, and it helps solve this problem of how does a miner determine how computationally costly a transaction is. But one of the downsides of a global metering model is that you need global consensus on the metering rules. So this isn't a show-stopping problem necessarily, but it does present a few challenges. So every single time that you discover that you need to update how your opcodes are priced within the EVM, you need to do a globally coordinated hard fork. So in the Shanghai attacks, where there was DDoS attacks taking advantage of mispricings in the opcodes of the EVM, we had EIP 150 that was included in a hard fork to help shift the costs a little bit. And there's been interest in third-party researchers analyzing how resource metering actually works in the EVM, highlighting certain attacks that you can try to construct based upon mispricings of the opcodes where they don't necessarily match up with the actual resources consumed. So that's one case study of how Ethereum handles resource metering. The second case study is, as I mentioned previously, I'm working on a project called LivePeer, and the core component of the video streaming infrastructure is a two-sided matching market where the requesters are broadcaster nodes that want their video transcoded, where transcoding means that an input video is going to be mapped to multiple formats so that you can play it on any device, and multiple bit rates so that it can be played on any connection speed. And this is actually a pretty costly process, so this is outsourced to orchestrator nodes on the network. And these orchestrator nodes play the role of service providers. So what we've been investigating recently at LivePeer is actually a local metering model, where this is in contrast with the global metering model used in Ethereum. And the benefits of having a local metering model is that we don't need global consensus for resource metering, so there's no need for network-wide coordination to make updates to that model. And the reason why that's useful is that each orchestrator, so each service provider on the network, can implement its own metering model. And then based upon benchmarks, or real-world performance, the orchestrator can always update how it prices the unit of measurement used in its model on the fly. So some more specifics about this metering model. The first question is, what is the unit of measurement used? So at first glance, you might think, why not just do time? So we already have fixed length segments of video that are being processed. So we can say that a 4-second video is going to be more expensive than a 2-second video. That might work. The problem with that is that when we're talking about transcoding, you have different renditions of each video, and depending on the output rendition, it's going to be more costly to do that processing. So a 2-second 720p rendition is not the same cost-wise as a 2-second 480p rendition. So that's a problem. How should the price differ between renditions? So a solution that we've decided to investigate is using a unit of measurement of pixels. So 720p, as I mentioned, is generally more expensive than 480p. So we can treat the expected payment for a single segment of video as the input pixels added with the output pixels multiplied by a price per pixel. And the pixels here is going to be derived from the height and width, which is going to be from the resolution of the video, multiplied by the frames per second, since a video is just multiple contiguous frames sequenced after each other, multiplied by the segment duration. And we can see in this small calculation at the end that you can actually try to reflect computational cost differences in the number of pixels. So let's take the example with 720p and 480p. If we do the calculation at the bottom to derive the n number of pixels that are actually processed in each case, we can see clearly that more pixels are processed in the first case than the second case, and that can help serve as an initial heuristic for the price differential or the cost differential between these two types of tasks. It's important to note that we want to meter pixels decoded and encoded. So this is where we have to get into what the transcoding workflow actually looks like. It's actually a multi-step process in the pipeline. We can ignore, in the diagram below, we can kind of ignore the muxing and demuxing step. We don't really care about that right now, but we just want to focus on the decoder and encoder bit. So any transcoding process is a 2-step process at the very least, where we're going to decode the incoming video, and we result in decoded frames, and then only then can we encode the video because we need to operate on the decoded frames. So there's a decoding step and an encoding step. And this is important to note for a metering mechanism because a 1080p input transformed into a 240p output is going to be more costly than a 720p input processed into a 240p output, even though the outputs are the same, because the output costs are going to be the same, but the input costs are going to be different. It's going to be more expensive to decode the 1080p input than it is to decode the 720 input. And you can try to explore the attack vectors here some more. A sneaky attacker could also try to stuff thousands of frames into a 2-second input. So let's say you're using time as your unit of measurement. Well, the 2-second input video could actually contain thousands of frames, drastically increasing your decoding cost, and that's not necessarily reflected by your unit of measurement. So the second point is, when should an orchestrator measure these units? So the first thought is, why don't we add a pre-transcoding step? So we can validate the incoming video, but the reason this is not ideal is this adds latency to an already latency-sensitive workflow. So if we're talking about a live streaming case, we obviously care a lot about latency. So you really don't want to add any additional latency before you actually do the computational service itself. Furthermore, if you remember the diagram that I showed in the previous slide, we do a decoding step as a part of the transcoding pipeline. And in order to measure how many units are going to be consumed by the decoding step, we have to do the decoding step. So if we add a pre-transcoding step for validation, that means we're going to do the decoding step in order to measure how much of the input we're actually going to process. And then we're going to do that decoding step again when we actually transcode the video. So some redundant work is going to happen in that case. So this is where we can actually draw from some of the principles used in the Aetherium gas model, in that we can actually try to short circuit the transcoding based on a running count of pixels transcoded. So in Aetherium, we have this out of gas mechanism where, as I mentioned previously, users are going to attach a gas limit to their transaction, which represents an upper bound on the amount of resources that can be consumed. Similarly, what we can do here, broadcasters, requesters in this network can provide a maximum number of pixels that are going to be transcoded as a part of this small transaction. And just instead of having a gas counter, we have a running pixel counter, and the end mechanism is pretty similar. We're just going to stop doing work when we know that we're going to consume more resources than we originally expected. So that was a brief foray into trying to define fair payments via resource metering. The second question that I had mentioned was quality of service, and one way to think about this is exploring combining micropayments with redundancies and failovers. So we want to protect the requesters from failure or quality of service degradation of any individual provider. So the first thought is, why don't we draw inspiration from, once again, proof-of-stake consensus protocols that oftentimes use a stake-weighted based selection to determine who the next block proposer is. So that's a useful mechanism in the context of proof-of-stake consensus protocols, but there's a couple of concerns when we're talking about service networks where quality of service is really important. What happens if the stake weights do not shift quickly enough to reflect the capacity or capability of any particular provider? What happens if the provider that you're consistently assigned to has a lot of stake, but it does not have enough capacity or it's geographically distant? So an alternative path to explore here is, instead of selecting one provider, we select n providers, where n can be a tunable parameter, and also make switching easy and low friction. So in order to make switching easy and low friction, we need to modify the payment workflow, and the way that we can try to do this is focus on micropayments. So the idea is to break up the computation into very, very, very tiny chunks, and then send a tiny micropayment with each chunk. And for anyone that's familiar with any of the work that Interledger has done with their packetized payment approach, this is pretty similar, where the idea is you make the amount of computation so small that the value exchanged is fairly small, and the value at risk is really small. So in the event of some SLA breach, such as the exchange not being fulfilled, we just reroute the work, and we do lose the value that was at risk, but oftentimes, hopefully, this is going to be something on the magnitude of fractions of a fraction of a cent. And then we demote the perpetrator in future selection. So if we have this switching mechanism and if it's low friction, we can try to explore alternate strategies for working with our providers. So there's two paths that we can explore here. The first is redundancies, and the second is failovers. And we need to decide, and which one is more appropriate really depends on the preferences of the user. So if you want to minimize cost and are okay with slightly higher latency in your use case, you might just fail over to another provider. If you want to minimize latency, but you're okay with a higher cost, then you might have n, where once again it's a tunable parameter. Providers redundantly process the same request, and then you use the first request. You use the first response to your request. And the key here is that you really do need to reduce the size of computation and reduce the value in each micropayment transaction in order to enable this seamless switching process. So that was a brief foray into how we can think about ensuring quality of service in the context of decentralized service networks using a strategy involving micropayments, redundancies, and failovers. And to wrap up, some interesting open research problems that I think can be good for future exploration. So on the resource metering side of things for fair payments, there's alternate metering models. It's not necessarily the case that the same metering model is going to be appropriate for every single type of use case. What could also be interesting is to jump off of some of the work that has actually happened in the blockchain ecosystems around creating VMs for smart contract platforms. There's been a lot of work in exploring metering WASM-based binary tasks. Could there be a world where we can leverage a WASM computation model and then meter the WASM opcodes? That might be interesting to explore. Furthermore, while I was talking about ensuring quality of service and using these different strategies for maintaining quality of service and avoiding service degradation using redundancies and failovers, what I skipped over and hand-waved away was, how do you actually pick the providers that you are going to fail over to? How do you actually pick the providers that you're going to redundantly send requests to? So I think there's different approaches to explore in this area, and the general theme is probably going to be some combination of Sybil resistance mechanisms. So in these service networks, we're usually talking about stake-based designs, with performance measurement mechanisms to score the providers for selection. So this might draw inspiration from some existing selection problems outside of the blockchain space, such as what certain users do for CDN selection, where they measure performance of various CDNs and then fail over to a particular CDN depending on the performance characteristics measured at any given point in time. So I think there is room for combining some of the learnings in both of these spaces in order to try to construct a provider selection algorithm, or at least a framework for constructing models for selection algorithms that could be applicable for a variety of service networks. And lastly, as I mentioned previously, there could be room for exploration in these opt-in, untrusted, transparent third-party matching services instead of having all decisions being localized to a particular node. So that's something that could be interesting to explore as well. And that wraps up my presentation for today. Thanks.